the pressure. So here we have some examples of from a book, and in this case what they are showing is the fact that they are extracting natural gas from a well located in the sea, and basically they use this type of ships to transport the compressed gas from one place to another. Okay? So, for example, here we have the places in the world where this type of operations occur, where they compress extracted gas in order to deliver to somewhere else. And then we have two types of natural gas and how it can be transported. First of all, it can be transported as a gas or a liquid. And then we can see which when it's transported as a gas is CNG, and as a liquid LNG, so liquefied natural gas and compressed natural gas, right? So in this case we can see the compression ratio. Normally if we transport it as a gas, it will be a lower compression ratio than if it is transported as a liquid, right? So we're not going to see this type of transportation, but we will see how we understand the compression and how we can calculate the properties of the fluid according to the compression work that we are providing into the system. Okay?
Which is 200 and 250 is bar.
Well, it is a ratio. So normally ratios don't have units. So it's, let's say if you have 1 bar, then you will end up to 250 bar. But it will depend on the units that you have. Okay, so it will be 250 times the initial pressure that the fluid had at the beginning. So basically what we want to know, compression will affect two things in the system. First of all, it will affect the temperature as well as the pressure, obviously, and in the case of gases it will affect the enthalpy as well. So last time we looked at the different types of compressors that are available in industry. This is just a small list of all the compressors. There can be more compressors that you can find. Okay. Here we have, well, what is a centrifugal pump, and this is normally used for liquids rather than for gases. So we look at this, and what I wanted to tell you is that there are three things that will comprise a compressor. Okay. It doesn't matter what type of compressor you work with. We will always have a suction, the compression part of it, which is generally what changes from one compressor to another, how we'll have the compressor force into the fluid going through it, and finally the discharge. Okay, so these are the three parts that will be involved in a compressor. Okay, so then we go to the next slide, and basically we already explained that last time, and we will again, most of our calculations will use an energy balance. In this case we have the enthalpy balance, and we basically work in sort of an adiabatic process, which is expanders and pumps, no heat is transferred to or from the fluid, only work. And then in compressors, expanders and pumps, the pressure and temperature of the fluid changes. So basically we have pressure and temperature changes throughout the system while the fluid is going through it. We said that engineers simplify calculations and will basically involve the consideration of this is an irreversible process by which we will have a constant entropy. Remember, when we're looking at the properties of entropy, we said that the entropy will remain constant whenever we have an irreversible process, and therefore that means that delta S will be equal to 0, right? So entropy of the inlet of the process will be equal to entropy of the outlet of the process. Well, this is an assumption that we will use to initiate calculations, and we will later correct it to actually get what will be the real effect of the system. We will see when we look at the example. So we have to take that into account in doing calculations. And here we have a temperature entropy curve. So if you remember, when we look at the entropy and the enthalpy, we look at the 3D curve, and later on we dissected that curve to produce a 2D curve. And this basically represents the phase change of the system. Okay, so what will be this area? What will be the fluid state on this area? On the, what will be your left-hand side? Yes. Here. Liquid. Here. Okay, saturation line. So you will have a mixture, liquid gas, and here vapor. Okay. So this chart is the same one we saw when we're looking at entropy enthalpy changes. Okay. So we're trying to reflect how these processes or these operations, such as pump, compression, and expansion, when we're going to look at how we calculate basically the work that we need or the work that we produce, where they are located. So first of all, if we are in the liquid region, we have a pump. We normally use pumps, and then on the gas region, we have a compression or expansion.
So in the expansion also gas, eh?
Yes. Expansion normally it involves a gas, because we said that when we change the pressure of a liquid, normally it's called a turbine, or you can have that process, but here we're going to look at processes, expansion processes only for gases, because they're the most interesting ones. Yes. Okay. So here basically, when we have a pump, when we're pumping a system, the changes are entropy. Here the slope, those seem similar, but actually the pump will be more of a straight line, okay? So the changes are very negligible. And also the changes in temperature will be very small. So actually this arrow will be very, very small. In the cases of a compression and expansion, normally these processes will involve very significant changes in temperature. So you can see how the arrow is a little bit larger. So that shows that the changes in temperature will be higher for the same pressure changes. Okay, so here we're dealing with a gas, and a gas is heavily affected by expansion or compression processes because it's a compressible fluid, right? So here we are, when we deal with liquids, normally we can take them as non-compressible and say, sort of, if we compress them, then it won't modify a lot the properties of that liquid going through it. So in terms of a compression, will imply an increase in temperature whenever we compress a fluid, and this is when we also saw in one of the diagrams, or perhaps we're going to see it, that always a compressor involves as well heat exchangers around it in order to control the temperature changes that happen. So when we have a compression, the temperature will increase, and when we have the reversible process expansion, the temperature will decrease. Okay? So, and the entropy will normally be affected as well more, so this slope will be more pronounced than this one. This will be very small, as well as the other one. So in here, we are looking at if we compress a gas, the entropy, what will happen to the entropy here through compression? What can you see? Here it was more or less at that, and what happens to the entropy? Increases. And when we were talking about the second law of thermodynamics, we said that entropy is, a higher entropy is a disordered molecules, right? Molecules that move higher. So if you have a gas that is more compressed, will molecules be more randomly disordered than if it's expanded? No, it will be the opposite actually. Because if you have a solid, it has the lowest entropy because the molecules are highly ordered in a solid. Then if you go to a liquid, the molecules move a little bit more, so it will be a higher entropy than a solid. And then if you move to a gas, the molecules are moving everywhere, so they are more disordered and therefore entropy is increasing. So here you will argue, oh, if I'm compressing, actually entropy should be decreasing because I'm making the fluid more ordered by decreasing the change. But here we should also take into account the temperature, the effect of the temperature. Not only I'm compressing this fluid, I'm also increasing its temperature. So because of this effect, we have an overall effect of an increase in entropy, okay? But just keep that in mind, that actually this is the effect of the temperature, but in fact, if we were compressing the gas, it will actually decrease in entropy. So whenever you first compress it and then cool it down, then we actually increase the entropy and then decrease it somehow, okay? Can you see that process going through? Right, so it's very important that by this stage you understand first and second law of thermodynamics. If you have any problems, tell me, because everything is going to be based on that. And this is just one of the diagrams that is used to express this type of changes. So here we are looking at these processes using this curve, which gives us the phases of a liquid, of a fluid. But actually we can use other type of charts. There are thousands of charts that we can use in order to explain a compression or expansion process. Another type of chart, which will basically show you more or less what is happening, because here we cannot see the pressure. You say, well, actually the main thing that is changing is the pressure, and pressure is not plotted in this diagram. Actually, pressure will be a set of curves like that will come into the chart. We cannot see them here, but if we look in other type of charts, such as this one, for example, okay, so this will be again an entropy and temperature chart, okay? And here we're actually not seeing the phase changes, so we don't have the actual curve where it indicates where we have. we are actually looking at a compression mechanism of air. So we are locating our curve already in the place where we will have a gas, okay? So we are just in that side of the temperature and entropy chart. And these curves that you see here, these are the pressure changes. So here we go pressure intervals of 500 kilopascals. So that means that every one of these ones will be 500 kilopascals of increasing the compression ratio of gas. And here basically by plotting the temperature and the pressure, we can know the entropy or the other way around. Okay? So this is just, I mean, you won't be using charts really for this module, but it's for you to understand them because a lot of the properties can be extracted from these charts. Right now we will focus on calculating these properties rather than actually looking at them. Why we said that a lot of these properties can be obtained in charts. Normally the charts are plotted for a single compound. Okay, so only air will be expressed like that, or certain compounds. But actually when we have a mixture of compounds in a fluid state, then calculations are the better way to approach the system. So here we have again the same type of system for the refrigerant 123, which is a type of refrigerant, a fluid that can be used in different applications in industry. And again, we have the chart, but this time we have enthalpy against pressure. Okay, so the X and Y axes have changed, and we're going to see what happens in this case. So enthalpy is normally constant when we have a pumping system. So in a pump, we'll have just a straight increase in pressure as you compress the system, which is basically what we look at in when calculating pumps. And then we can have a compressor. A compressor will involve both things, a change of pressure and a change of enthalpy, which is closely related to temperature. So basically in a pump, the temperature changes will be very minimum, and therefore the enthalpy will be kept constant during it. While in the compressor, we have the two effects happening. And here we can see a photo of a compressor, and compressor is here. It's the blue thing that you can see at the back of the tube, and here will be the gas inlet going through the compressor, and then we will have the outlet over here. So if you see, this is the exit of the compressor, and that's the outlet of the compressor. Okay? In this type of system, we have actually a recycle system. So the recycling is used sometimes in order to further increase the pressure, or just to help us regulate the compressor in terms of achieving the pressure outlet that we want. So significant gas and vapor heaters occurs in a compressor, right? As we said, and particularly if the efficiency of the compressor is low. So basically if we have a highly efficient compressor, we don't have any energy losses through the heating of the fluid. But then if the compressor changes in its efficiency, most of the energy will go into heating, and a minimum amount of energy will actually go on the fact of increasing the pressure of the fluid. So we normally assume that a compressor behaves adiabatically. Okay? But we also recognize that a compressor will occur certain losses. So we initially assume that a compressor behaves isentropically, so it's an isentropic process. But then later, in order to, this will help you calculate the work at isentropic conditions, but in order to get the real work that you have in the system, you need the isentropic efficiency. So actually, by dividing the work that you have calculated at isentropic conditions, so looking at or the first assumption that is an irreversible process, what does isentropic mean?
Constant entropy.
Huh?
Constant entropy.
Constant entropy, and we say that when we say constant entropy, it's for irreversible processes, right? So this is an assumption that we say. So we will first calculate the isentropic work, and then we will actually expect to know the isentropic efficiency in order to actually calculate the real work. So this equation is very useful because it relates the assumptions that we may use in order to facilitate our calculations of assuming constant entropy. So a reversible process, and then being able to obtain from that, using the efficiency at that conditions, the real work. So normally the typical values of the isentropic efficiencies for pumps, expanders, and compressors are in the range of 0.6 or 0.9. That will depend on the type of system that is operating. In expanders, we use the same relationship but actually we switch the numerator and denominator of this equation, and then we actually have the work over the isentropic work that is calculated. So again, we can obtain the work, the real work of the system, that is produced in the system in this case, by multiplying this isentropic times this efficiency times the work. So obviously what is this equation saying? That because of the efficiencies that we have in a compressor or in an expander, once you calculate the isentropic work, you will require more work actually in real life. Can you see? Because this will be less than 1, therefore this will increase. Can you see that? However, in the expander, once you calculate the isentropic work, you actually will produce less work, right? So in a compressor, you will need more work of what you have actually produced, what you actually calculated you need, but in an expander, you will produce less work than what you have actually calculated you will produce. And that's just to take into account the inefficiencies of the systems. That's why we modify this calculation. Otherwise, it won't work the same if it was the same type of calculation for the two of them. So the isentropic process is a reversible process which achieves the same pressure increase as the real one. And it is called isentropic because the entropy of the gas entering the process equals to the entropy of the gas leaving the process. So delta S will be equal to 0 in this case. So let's have a look and let's try to explain this if you want. Let's try to explain it using a chart. Sorry?
No, we are asking about this.
Previous slide.
This
It's not
one?
clear. Is
This
it?
one?
No.
Yeah, the previous one, the printed
Ah.
one.
This one?
Yeah.
Okay. So, this one?
Yeah,
These two
no,
equations?
The sentence. The
Yes.
isentropic process is a reversible process.
Mm-hmm.
Yeah, we discussed it's an irreversible process, isentropic.
No. It's a reversible process.
So what?
So that means that the entropy Okay, if you had a process going towards one direction, you will have a certain amount of entropy, right? So let's see, if we go from liquid to gas, you produce a certain entropy. And then if you go from gas to liquid, you produce the same entropy. So S1, that is going from one direction, will be the same, and S2 going from the other direction. Therefore, delta S will be 0. So it's a reversible.
Yeah.
Perhaps I said did I say? No, irreversible. That will mean that you will have different entropies if you go forward or backward, because it is irreversible. So you cannot come back to the same state that you were having from one direction to the other. For example, an irreversible process will be using producing work out of heat. It will be very difficult. It's very easy to produce a certain amount of work with heat, but doing the opposite, the same work won't produce the same amount of heat. So that will be an irreversible process, because you'll actually end up with different conditions.
Is it irreversible or reversible?
No, in that case it will be irreversible, because you end up, if you convert, let's say if you have mechanical work and you convert it to electricity, you produce electricity from mechanical work. You cannot then induce electricity and have the same mechanical work. It doesn't work like that, because that's an irreversible process.
Okay, but in this case, what is it?
We are assuming that it's a reversible process.
Okay, so for the work isentropic, it's the same amount, yeah?
No, we are obtaining the work at isentropic conditions. So this is work at isentropic conditions, and that's work at real conditions.
Okay, what's the difference?
That in this case, we are assuming that this is a reversible process. And in this case, we are accounting for the irreversibilities of the process. Why? Because why will make the process irreversible? The efficiency. You will here we are assuming that this doesn't have any efficiency involved into it. So it's 100% efficient. We can go forward or backward without losing any efficiency. So that's why we say that it's isentropic. But we know that all the processes have an efficiency. That is very hard to have a 100% efficiency process. So that's how we get the efficiency, and we can actually obtain the work, the actual work.
So these values of efficiencies for the compressor and pumps, as well as the expander, is measured for a reversible process.
Yes, yes, but it helps us obtain the actual real work that we will need or we will produce. Is that clear?
Fine.
So basically, here what we want is the real work, in this case, that we will produce in expanders, and for compressors is the work that we will need. But can you see why the equations change from one to the other? Is that clear or not?
You have
The expander actually needs less work
less work.
to decrease pressure. It's coming
The expander will produce less work because of efficiencies than what you actually have calculated as using isentropic conditions. And the compressor will need more work than what you actually have calculated at isentropic conditions. Okay? So yes, this actually comes from the second law of thermodynamics. A reversible process will always have delta S equals to 0. Okay? So it's basically assuming 100% efficiency of a process. Is that fine? No? So hopefully this will not confuse you more, but imagine that you had an entropy and an enthalpy plot. Okay, so the entropy enthalpy plot, then you have these pressures. We saw in the part that we had normally the pressure expressed like that. So you want to go from pressure 2 to pressure 3, right? So you want to compress the gas that you have in this case from pressure 2 to pressure 3. So you have a certain entropy and a certain enthalpy for the inlet conditions. And this, so that this is the inlet condition of their fluid going through the system. So the first thing that you're going to do is assume isentropic compression, a reversible process. So then you go straight in this line, okay? So the entropy remains constant in this case. So you have the same entropy at the inlet and at the outlet of the place. So then you arrive to a point where we can say that this will be HT3, but then let's put that because this is taking into account the assumption that we have made. But actually, that's not in fact what happens. So in fact, what happens when you compress a gas, you don't move straight, you actually have this type of movement, right? So you obtain this pressure, but actually because of the changes of the temperature that is affected on the fluid, we actually increase the entropy of the fluid and we increase the enthalpy because of the change that happened, H2,3. So in this case, we are actually taking into account the friction of compression, okay? Friction of compression or efficiencies of the system. Efficiencies. Right? So what we're going to do in our calculations is first we're going to move to this position and we're going to obtain the conditions here. And after that, we'll move to this position using the efficiency of the system. And then we'll arrive here and then we'll get actually the work that is needed and the temperature that we get. And that's what we're going to do in this example, okay? So in this compressor example, we have 0.5 kilograms per second of propane at that temperature and pressure are compressed to 500 kilopascal in a compressor with an isentropic efficiency of 80%. The gas obeys the virial equation of state. So in this case, we need to calculate the work done during compression and the temperature of the gas after compression. So in most cases, we can assume an ideal gas, okay? Unless basically it is mentioned that we need to use the virial equation of state, which is normally used when we want to obtain very high pressures at the outlet of the system. This is going back a little bit when we were looking at changes in entropy and enthalpy, when we look at the virial equations of state and how the volume is basically expressed when we have this type of approximation. Okay, so this is the same approximation as the ideal gas law that will correlate volume, temperature, and pressure. So if you were taking only this part of the equation, that will be actually the ideal gas law. But here we add a factor in order to just account to certain non-ideal conditions of the system. Okay, so the only thing that changes here is this B over M, if you look at the equation. So here we actually have the value for B over M, and then we have the heat capacity of the propane at this condition. So we always said that we were going to start our calculation, first of all, assuming an isentropic process, right? So if we have an isentropic compression, then the entropy of the inlet will be equal to the entropy of the outlet. Therefore, delta S equals to 0. Okay, so the entropy of the inlet is equal to the entropy at this condition, 298, which is basically the condition where this one is entering the system. Okay? So we can use the same property equations that we saw last week. So this is just going back at the property equation. So here we have delta S equals the changes of temperature and the changes of pressure, how the entropy is affected by this type of fluid properties, right? So in here we have the partial derivative of the volume over the temperature, and then we will need to express this equation in a different way in order to be able to do the derivative against pressure. How are we going to help us change this basically part of the equation? What do we use here? The virial equation of state. Okay, so the equations of state help us do the differentiation or differentiate this part against pressure, because it relates volume to pressure. So you are able to basically express the changes on volume over temperature against something related to pressure and help us on the calculation on this side. So then we get the virial equation of state, and basically the virial equation of state will help us relate the changes in volume against temperature using the equation that we saw previously. Right? So using the known values, we basically are able to substitute what we have in here. So Cp was given over T dt, and then we substitute the virial equation of state. If you remember, 1 over m dV over dt was given as well, and this can be obtained from R. We know what is R, and the most that goes through the system. So we basically just substitute the data in this equation, obtaining 1.5 over T dt, and then the integration will be from the temperature inlet, which is 298, to the temperature outlet, and this the pressure will be integrated from 101 to 500, which is the pressure that we actually want to achieve in this type of system. So if you see here, well, pressure is over here, so you can easily solve this integral as well as that one. So both of them will basically require the natural logarithm of the variables. So here we have the integral solves already. So we are substituting this part of the equation, 1.5 natural logarithm of T out over 298, which is the temperature at the inlet. And then here we have the pressure changes. Okay? So in this case, we know that the entropy at the outlet will be equal to the entropy at the inlet because of our assumption at the beginning. So this can actually go to the other side and will give delta S and will be equal to 0, this equation. And we're able to take out the temperature and solve for the temperature. Is that clear? Why don't you do this step, going from this equation to the actual temperature, and you tell me if you get the same value, please. So I'll give you 5 minutes to do that. Okay, so we said that we were going to solve for this part of the equation. Is everything before clear? How we got from the beginning to this equation? Is that clear? Is that clear? So we've arrived here, and then we move this one to the other side, and then we generate delta S, okay? Since it's isentropic, then that's equals to 0, and then we have all the other side of the equation. So we just basically solve, we move this one here, we do the exponential, and then we obtain T out of the system. Right, so does that result make sense for this type of operation? Is this T out higher or lower than the temperature at the inlet? Higher. Does it make sense for a compressor for the temperature be higher at the outlet? Yes, so therefore it's likely that it's correct. So it's a way to verify that actually you didn't get something that is not right. Okay? So that will be the temperature at the outlet, but under isentropic conditions. Okay? So we need to refer that this is under isentropic conditions because actually it won't be the real temperature at the outlet. So we continue. Now we need to correct. We have obtained the T out at isentropic conditions, but actually we want the T, the real temperature that we will get. So we continue in our calculations. So we will use this temperature now in order to calculate the enthalpy after isentropic conditions. Okay? So in this case, we will use the enthalpy measurement. So it's the same, taking the equation of the enthalpy property that we saw when we were looking at enthalpies. So we have CPdT. We said that the only difference between entropy and enthalpy was the temperature dividing in here, if you remember. That's the only difference, basically, between one and the other. Okay, so here we have just Cp dt, and we have the integral as well of the real equation of state that we saw in order to approximate actually the volume, no? To be able to derive the expression. So again, we get into...
So is it the same previous one? Where did you get 3? This was temperature.
Yes, that's the temperature. So now we're actually doing the
366.
temperature of the system. So we need temperature here.
Yeah.
So we're actually using that temperature.
Why it's minus? Why it's minus?
That comes because of the equation that we saw of the enthalpy on the lectures. B over M dV over dt, dV over dt. So that will be minus. Okay, hold on with me and then I'll let you know when we have the break. Actually, we can have the break now while I investigate that. So let's continue at 10 o'clock.
Yeah, that's why I'm not happy.
It is minus because it comes from this equation. So in here we have V minus T dV over dt. So the minus comes from here. And that's the enthalpy, changes with temperature and pressure. So it's on the first lecture notes.
Why you said 0?
In that case, because we were actually moving, if you remember, when we were solving this equation, but it's not actually crossed all the time.
For enthalpy. Where did we get to 0.5? When we're calculating this? It's mass, yes.
Yes. That's the mass. That's the energy balance, actually, of the system.
Because she was saying that you should rearrange. Yeah, you should change your I changed it, which is
Isn't that the correct system?
yeah, that's right.
Oh my god.
You just take it away. Yeah, it's paper. Okay. No, actually.
Everything in it.
Yeah. 3, 10, 11, 12, 13. Then after 13 should be 4. You should check my order. It should be after 3. Well, 13.
No.
I missed the lecture last Monday.
You didn't go?
No, I missed it. So I just went through.
Yeah.
I assume, did you finish off the slideshow from the first week on enthalpy and entropy,
Yes.
and then
Those are
just
done.
start this one?
I know. We actually did the heat exchanger.
Yeah, the start of the flow process is.
Yes.
Just
Last
that
week.
one. Yeah.
Last week, yeah.
Okay, that's all you went through last week.
Yes, but you can see the recap
Yeah,
in Blackboard.
I got the handouts. I don't remember all the handouts, so I just went through them.
Okay,
but I'm up
yes.
to
We
here
just
anyway, so-
arrived to. We just saw heat exchangers last time, and
Yeah, I've done this
we-
example, so.
Okay,
Yeah.
so then they're
All right, brilliant. Thank you.
Right, so let's continue. Okay, we'll continue. So basically, we are now obtaining the delta H. Okay, so enthalpy will actually change. Why will enthalpy change? Well, it's just actually a function of temperature. So if temperature changes, enthalpy will change. So the only assumption that we started is that it's an isotropic process, and therefore entropy is the one that remains constant, not enthalpy. So now we're going to obtain the changes in enthalpy under isotropic conditions, and for this we need to refer to the equation for doing delta enthalpy that we saw last time. So it's basically this equation, but without this one cross. That was for the example that we solved last time that we taken. Okay, so in here we have a negative value, and that's why it becomes negative here. So this comes from this equation. So we basically solve it we're using the virial equation of state again. That was the approximation that we were asked to do. And we obtain the delta H. So these steps are going through the integration again of all the variables, and then after that just substitution of the variables in here. So 1.5 T2 minus T1, and in here we have P and P2 minus P1 and all the constant that we can see in here. So that will be delta H. But what type of delta H will this be? Will this be the real delta H that you have in the system? No, it will be under isotropic conditions. So if we look at our chart that we were seeing before, we are actually here, right? This is the delta H that we are first obtaining, right? But actually we want the delta H of this. So we still don't know that one. So in this case, from the delta H that is obtained, we actually can calculate the work that is needed in the compressor using a simple energy balance, right? So in this case, the work equals to the mass times the delta H under adiabatic conditions. So we don't have any heat going out or anything. It's just within the system. All the heat that is produced is going to work, basically. And we are able to obtain the work that we require in this system, right? So after that, we move on from isentropic conditions to the real conditions. So we said that in order to modify these, we actually use the efficiency, the isentropic efficiency of the system. So we divide the work that we obtain over the efficiency, and then we get the real work. If you see, the real work will be much higher than the work calculated. So actually, well, we get 61.5, and that will be kilowatts that we need in order to compress this amount of propane. Okay, so now we have obtained the real work, but actually we need the real temperature as well that the system will live at. So to find the temperature, what we'll go backwards this time. So from this real work, we'll calculate the delta H using the energy balance. Okay, so we use the energy balance in this case, and we obtain the delta H real of the system, which will actually be higher than the delta H calculated under isentropic conditions. So that delta H will actually be this delta H, right? And we can see how this is higher than the one at isentropic conditions. So from the delta H, then we'll go back to the equation of state, and from here then we make temperature our variable, and we solve it for the temperature, and we get the temperature of compression of 382.9 kelvins. So let's have a look of what we did in our calculations. So the first thing is that we assume isentropic conditions. So we calculated the temperature under isentropic conditions. From here, using the equations of state, we were able to obtain the enthalpy under isentropic conditions. Then from the enthalpy under isentropic conditions, we obtain the work using an energy balance. After that, we change the isentropic conditions to real conditions using the efficiency that was given in the problem. Okay? And then from the real work, we went back using again the energy balance, and we obtained this time delta H for the real system. And then using the property of the equation property for fluids, we went from the delta H to the real temperature. So we have work, delta H, and temperature for the real conditions. Right? And this was solved for a compressor to obtain work, delta H, temperature. So in this system, we can solve it for different things. Okay? So anything from this set of equations can disappear, and you should be able to obtain it as long as you have enough variables defined on the other system. And this is going to be the approximation that we are going to use in order to calculate compressors. Okay? So there are different ways of actually calculating this compressor, and we will see there are other approximations which take into account the polytropic efficiency, where we have gamma involved. We will discuss about that, but we are not going to use this type of approximation for obtaining the conditions. So now let's go and explain the expander example. Okay, so we're going to do the opposite from compression, and this time we will calculate it for an expander. So in this case, the example says we have 0.05 kilograms per second of air, which are expanded from 620 kilopascals and 295 kelvins to atmospheric pressure, 101 kilopascals. If the expander has an isotropic efficiency of 85%, calculate the work done by the expander and the temperature of the air after compression. So the air can be assumed to behave as an ideal gas. So this time the equation of state that we're going to use is just the ideal gas law. And we have the mass and the heat capacity of the expander. Okay. So just by looking at this, it is an expander, so it's asking you to calculate the work done. So how are we going to calculate the work done? what is the main equation over the last steps that we will use? If you remember, to calculate the real work, we will use this isentropic efficiency, okay? So the first thing to detect here is that we will need to actually take into account this efficiency, but not using the same equation as for the compressor. It will need to be switched, right? That's very important because sometimes it's very easy to get confused and use the same equation for both, and it's not the same equation. And then they want the temperature, right? So the first thing to say is it is an expander, so the temperature, will it be lower or higher than the inlet temperature? Lower, okay? So we need to, that's the first thing that we need to remember when we do calculations, to actually check that things make sense, okay? So let's have a go. So we have the expander, and we'll draw first of all see if I can.
Poetic entropy.
We are again assuming an isentropic process the same way as the other way. So it will be the kind of the same equation.
The same equation, but
A similar equation, yes. So I'm going to draw the diagram. Try to solve it as well by yourself as you go along. Okay, so we have the main equation to approximate the fluid properties, and this time we will need to solve this part of the equation where we have the equation of state. So V will be equal to RT over PM, right? So in this case, dV over dt will be equal to R PM. So we will substitute that into the integration. And then Rm go out of the integral because they remain constant. Yeah, so you integrate dP over P. Okay. So now we were given already Cp. And the mass Okay. So now let's solve this. So you have T and P at the bottom, so that will be natural logarithm again, so it's the same way to solve it as always. So I'm just going to substitute CP in this case. And then you need to take out T Eisen in here.
T should be 195.
Where? 195? No, 295, right?
No, I mean the answer.
Oh, how much do you get? T Eisen. No, but that's a real T. The answers are for real conditions.
Oh, okay.
Mm-hmm.
The answers are for real conditions.
Mm-hmm.
Okay.
Mm-hmm. Yes, so it's the final answer. So first we'll get T Eisen, just the same way we did it for the other one. So how much you get here?
176.97.
177? Mm-hmm. So after this, we will go and now calculate delta H for isotropic using the T isotropic, okay? So you will have this equation. Sorry, is everyone over with this one? Right? So we will substitute in this case this volume and that one. So here we say volume equals RT over PM, right? And then for this one, we say T dV over dt P equals TR over PM, right? Can you see that? So this will be RT over PM, and this one TR over PM. So once we substitute this, then what happens? It's 0. So all these gets cancelled out actually for ideal gases normally. Okay? Can you see that? So for an ideal gas, the changes in pressure are not considered because of that reason. So then it becomes very easy because it's delta H isentropic will be equal to only 295 T-Isen, how much was T-Isen? 177. And then CPDT, which is equal to 1080,177 minus 295. Okay? So how much do you get here?
120,360 minus 120,360
Minus 2. Let me just do it. One, 20360. What will be the units of this one?
Kilojoule.
Joules
Kilojoule.
per kilogram. Okay. Okay. So what do we do after we get delta H asymptotic? Okay. So we use energy balance. So in this case it's 0.05, right? Well, it's a little bit. Do you get this value? So minus 60,000 watts. Okay, so now W real will be equal to N asymptotic times work asymptotic. So that will be 0.85 times minus 6018.
See.
5116. Negative, right? Because we're producing work in this case. So now we need to get the actual real temperature. So what are we going to do now? Work backwards, right? So now we get delta H real using the energy balance. So W over M. That will be plus. Right? 195, so
It's only for
so
one
it's more or
stage.
less the same way, but we only need to consider how the equation works to work out from W isentropic to W real, and just check that this temperature will actually be lower than the inlet one, so that is fine.
Then for multi-stage, is it same? I mean, same state for the multi-stage compressors. Like,
Yes, so it will be for every compressor doing the same calculation again and again. But when you get for multi-stage compressors, you normally use software to help you out in your calculations. Won't be doing all of this by hand. Okay, so talking about multi-stage compressors, here we have an example of, first, before going to multi-stage, we'll go into compressor and expanders using the polytropic efficiency. So this is something that you may look, I'm not sure if somebody has already seen that in their previous degree, but this is another way to actually calculate what we have seen. And in here, we basically take an approximation, which is gamma, which basically explains how the process behaves, or what type of curve the process generates regarding of the system that we are working on. So for air, we will have a type of curve. For different types of gases, we will have an approximation on how volume changes against pressure. Okay? So for an isotropic process, then we have this approximation, this curve. And then how are we going to approximate that? Then we take the relationship of pressure volume, and then we normally use an exponential, which is gamma, which is the ratio between heat capacity at constant pressure over heat capacity at constant volume. And this is another type of approximation that we can use as well for in our calculations. Especially, sometimes this is used when we actually want to know the volume after a compressor. So if we have an inlet volume and we want to know the outlet volume of the gas after the compressor, then this type of approximation is very useful because it gives a relationship between pressure and volume. And therefore, if you know the pressure that you are compressing that gas, then through this approximation, you can immediately know the volume of this gas at the end. Okay, so it's very useful when you want to know actually volume at the outlet of a compressor or volume of the outlet of an expander using this type of approximation, right? And this gamma will change depending on the curve. So we have said that this is for an isentropic process, but then we will have a PV 0.5 to the power of 0.5, this curve for a certain type of gases, and this one for other type of gases. So usually air will be, for air we will have a gamma value between 1.4 more or less. And for most processes it will involve, for most gases it will go from 1 to 1.4. Okay, so here we're looking at really extremes, fluids that will behave very differently. We can also look at the polytropic efficiency, and it's more or less the same way as the isentropic efficiency, but again using this type of approximation in the end instead of just this gamma Cp over Cv. Then we will have this polytropic efficiency of the system and this type of approximation if we want to obtain changes in volume in the compressor or expander. So we are not going to go into detail of that since we are only using the fluid properties in terms of entropy and enthalpy to help us our calculations, but this is something you can come across in a textbook or perhaps you have looked at it previously. So now let's have a look at multi-stage compressors. Okay, again, I think that asking you to calculate a multi-stage compressor by hand will be kind of, could take you the whole semester. but really you need to know what are the key things for multi-stage compressors, right? So why are we going to use multi-stage compressors? So as we said, every time we compress a fluid, we will have an increase in temperature. There are some times where we cannot actually have these increases in temperature in the fluid, so we cannot allow for the fluid to go to the temperature, okay? So for example, in other things, it might damage the equipment by itself. If the compressor might work well, but the increases in temperature might just affect the whole compressor system, or it might be dangerous for the fluid that you are actually handling to go to this type of temperatures. So in this case, we will have this type of compressors coming together, and here what we're basically doing is that we are controlling the temperature. So we do an incremental increase in pressure, so we're all the time applying pressure and more pressure to the system, but the temperature will come back to the initial conditions through a heat exchanger. So I compress from P1 to P2, and then I increase the temperature to T2, but then I use the heat exchanger to come back to the inlet temperature, and therefore just have the pressure changes again, and then heat the system as well to come back to the inlet temperature. Okay. Obviously here the work that you will need from work 1, work 2, work 3 will decrease, because the system will become more efficient, having these temperatures of the inlet, as well as every time you will need less work in order to achieve these pressure changes that you want. So in this case, well, how do you actually decide whether to use 2 compressors or whether to use 3 compressors? So what will be the inherent disadvantage of using a multi-stage compressor towards using only 1 compressor? What is the disadvantage that you can see here
Disadvantage.
of using multi-stage compressors?
There is no disadvantage.
So if you were
increase pressure.
the disadvantage, if you were actually designing a plant and you were telling the investors you need to pay 3 compressors instead of 1, what do you think will be the disadvantage? Cost. So they will tell you, please, I just want 1 compressor. I don't want to pay for 3 compressors.
But you can put 3 other to do in 1 compressor. There will be stages. You will have 1 whole compressor, but with a stage.
Oh, well, there are different compressors that allow multiple stages as well.
Yeah.
However, those are quite expensive actually.
Yeah.
They are even more expensive than multi-stage compressors because of the fact that it involves a lot of engineering as well as maintenance involved on it. So actually what we will need to do is that we will need to do a sort of a plotting of cost against efficiencies. Okay, so the first of all is that we may have the constraint of the fluid properties that we cannot heat to that temperature, so therefore we need this type of compressor. But then again, when we have multi-stage compressors, we can have a higher efficiency than only 1 compressor. So that means that having 3 compressors to get the same pressure will be more efficient. You will lose less work in heat. You will use more efficiently that, but then you will have to use more compressors. So what we actually do is that we input this type of equations into a software system and compare the use of 1 compressor to the use of 2 compressors, 2 to 3, and we plot cost against efficiency. Okay, and then we obtain a place where we actually get across on the 2 values, where we obtain the amount of compressors that we need in order to get the best cost benefit and the best efficiency of the system. And this is not normally done by hand. You normally input that into a software, which we will use later on this towards the last stage of this module. and then that will help you to actually approximate what will be the best possibility for your type of pressures that you want to obtain and the efficiencies of operation. So here we have the total work will be work 1, work 2, and work 3 added together. Okay, and the temperature is reduced to T1 after each stage. So basically the changes in pressure will be equal in each one, and we will have to 1/3 in this case. So for the general stages, we can just generalize this equation to that, and after that solving it. But we won't go into detail for this. Okay, so finally we come to, we have seen how to calculate the system for a compressor and an expander. Compressor and expander are normally for gases. So let's now have a look at the pump example. Okay, how we obtain the work that is needed to pump a liquid. And in this case, we're going to look at it towards the changes in properties. So we have 5 kilograms of second of water at 298 kelvins, and these are to be pumped at a pressure of 101.3 kilopascals to 800 kilopascals. So again, we're given the isentropic efficiency of the pump, 75%, and we want to calculate the work done by the pump and the temperature of the fluid leaving the pump. So first of all, how do you think the temperature of the fluid will change in a liquid that is being pumped? Increased temperature? Very little. Very small increase in temperature, right? Because this is a liquid. So we have this data that was given to us, and then in here we will assume that the volume of the liquid is constant, because we are talking about an incompressible gas, an incompressible fluid, and in this case the property relations of S and enthalpy becomes easy, okay, because of these facts. With this assumption, there is no temperature increase during isentropic pumping. So ds equals to 0. So as there is no temperature increase, the enthalpy change becomes dH equals VdP, and then delta H, basically we have the volume times the inlet outlet pressure that we want, and the inlet minus the inlet pressure. Okay, so we solve for the pump like that, and then we get this enthalpy. So let's calculate the real work done. So in this case, we will have the enthalpy over the isentropic efficiency, and that will actually be the real enthalpy that we have for our system. So the work of the pump will be the mass times the enthalpy, the energy balance, and that will give us 5.03 kilowatts. So let's try to solve it. Here. Okay, so we have a pump. Okay, so we will first assume an isentropic process. So ds equals to 0, Cpt dt minus dv dt.
What's 1.07? Is it like real?
Which one? 1.07? Yes, it's the real enthalpy that you actually have in the system. That helps you to obtain the real work done. So it's a little bit like, instead of going to, this could actually be work.
Which one?
Well, this is the isentropic enthalpy, and you divide by the efficiency that was given into the system to actually give you the real enthalpy, and then you just multiply that by the mass, and that's the real work, m delta H. But going to explain it better this way. Okay, so we have an isentropic process, what we have assumed as always when we increase the temperature. So in this case, for liquids, the volume is assumed to be constant. Okay, and this is something that we should look at if we can actually make this assumption for the fluid that we are pumping. And if not, then we will have to use a property again, a property equation in order to be able to solve this. And normally we will go through cubic equations to approximate that for a liquid, okay? But since this is a liquid, we are actually assuming that in this case. So because we're assuming that, then this goes to 0. And actually we have 0 Cp over T dt. Okay? So we have 0 Cp is 4.21 kilojoules per kilogram Kelvin over T dt. Okay? And here we actually have a system where we need to equal this equation to 0, and then we have a T dt. So in this case, T of the inlet, okay, will this T be 0? This T won't be 0, right? So this T will be higher than 0. Therefore, in order to get 0, what needs to be 0 here in this equation? dt needs to be 0, right? And if dt is 0, what does that mean? No changes in temperature. So that will be temperature of the inlet equals temperature of the outlet. And this is the statement of that the temperature doesn't change in this case for the isentropic work. So therefore, the temperature, because all this is isen, no? We're calculating it using our assumption. So this is temperature for isen. So the temperature of the inlet will be equal to 298 kelvins of the temperature of the outlet. Can you see how this was obtained? Okay? So now let's go and have the isentropic work. So now we're going to get dH. dH equals Cp dt plus V minus T dV over dt dP. Okay? So we said that the volume is constant, so that goes to 0. Okay? That was our assumption. And then we say that dt, what happened to dt? Is 0. So then dH will be equal to V dP. Right? So delta H asymptotic will be equal V delta P, which is 0.001 cubic meters per kilograms, 800,000 minus 100,300. So the delta H for the azeotropic process, I think that should give you something around 755 joules per kilogram. So then we go into the work, and then go work Eisen over the efficiency at isentropic conditions. So again, we just input the energy balance, which is 7 times m delta H over 0.75, and that will give you watts. Okay, so 5.03 kilowatts.
We multiply it by 5 here then.
I'm just here taking out a step. W equals m delta H. W equals 5,755. Right, so it's just having here the energy balance into the equation already there. Can you see that? So that will give you 700 and so that will give you 3,775 joules per second, and then just divide by that. So can you see we're using the same approximation we use for compressors? Right? So this is a little bit of an explanation of what is summarized in here. This doesn't explain a lot how to go through the steps, but that's basically what is happening. Okay? So now we're going to actually take these values to obtain, again, go backwards, the real enthalpy change and the real temperature at the outlet. Right? So first was isentropic, and then we took the real of the two of them. And then for this, well, what we do is that we have now this work done by the pump. So now we go backwards and we calculate the enthalpy, the real enthalpy, okay? So we take the mass times the work over the mass will give me the delta H real. Right? Is that clear, or do you want me to write it down? And then delta H real will be 1.7, that is over here. And that I will use again the same equation that was used previously in order to obtain the temperature, but this time the temperature is unknown because it's not azeotropic anymore, so we don't know what is the temperature. And then we have the temperature at the outlet of 298.1 kelvins. Okay? And with that we can actually calculate again, using this temperature, the actual entropy change of the system. So what was the temperature at the inlet? 298. And the temperature at the outlet? 298.1. So really it's the same. The temperature changes were quite insignificant. So actually we don't use this type of equations for pumps because of the properties of the fluid don't change a lot. Okay? So perhaps you're familiar with fluid mechanics and you say how a pump was obtained. But in this case, basically what we mainly use to calculate pumps is the mass, the volume of the liquid times the delta pressure over the isentropic efficiency, or the efficiency of the pump. Okay? So normally we can use this type of equation to get the real work and not go into calculating the entropy, the enthalpy, because of the changes that are quite small, and engineers normally assume that it's the same temperature at the inlet at the outlet. Right? So I'm going to stop here, and next time we'll go through the valves you can see here that there is an example of valves. So I will suggest that you go through this example by yourself, and then on Monday we'll go through the example together. And again, go by yourself through all the examples that we saw today. In case you have a question tomorrow, we still have 1 hour for these flow processes, next Monday. For these flow processes, we still have an hour. So we have plenty of time to ask questions. So this part is quite clear for you before we go into multi-component mixtures, okay?
Why
T needs to be 0. No. T is equal to T outlets. T is not 0. T is not 0. Delta T is 0.
why it's
Because we have this equation, because we have assumed that it's an isentropic process, right? So because it's an isentropic process, this needs to equal 0, not changes in entropy in this case. And to make these changes, to make these no changes in entropy real, Ct has a value, T has a value. So therefore delta T has to be 0, and that's why there's no changes in temperature.
and you said if the T is over 0, then what did you say about it?
This one is just to actually explain that this equation has to be 0, but T is higher than 0. So T has a value that is at least the inlet. So therefore this cannot be 0. Okay?
Last week you said we're going to help us look at universal constant.
Which universal constant?
When you were talking about liquid,
Which one? Yes, the one that's... Yes, I couldn't find... Which was the equation that you told me?
it's on the mixture.
Oh yes, it is. No, I haven't looked at it. It's just I forgot. So which was the equation?
This universal gas constant.
Oh, so what is R? Okay, I'll get it for next time. Sorry about this, but yes, I'll look at it. Okay.
Talking about the efficiency.
Yeah.
How do we get the efficiency? Is there a chart? Like,
The isentropic efficiency.
yeah, before we, how do they calculate the efficiency? Like, we are designing. How do they get the efficiency before? Is there a
So,
formula?
yes, the problem is that you can get that efficiency, but you will need to know the temperature and the inlet, the temperature of the outlet. So you actually will need to measure that and then obtain the isentropic efficiency.
So, like, the 75%, the 5%,
Yes.
temperature.
I think that normally when you are designing it, you basically need to know how much the temperature is going from one place to the other. So it will be through testing the system and then knowing that, because you will need that variables. If you use this set of equations and you don't know the temperature of inlet, outlets, and these calculations, then you cannot solve it, to say that. You can make some examples. So let's say if we have here this system and we have, where is the isentropic? Here is where we have the isentropic, no? So I could ask you, calculate the isentropic efficiency. I could ask you that. If I give you the T at the inlet at the outlet. So, yes, so you could calculate the isentropic efficiency if you actually had the temperature real and the temperature at isentropic conditions. And normally for fluids, we can then go and have isentropic, get the pressure that we have, and then know the temperature. So it will be through these relationships. So this is actually another way of putting the same problem, but calculating other variables. So why don't you try it? Why don't you try to take out the isentropic, use the other values, and see how you will manipulate the equation? Yes, it will be good, I think.
One more question. Why this should be less than 195?
Where? In the,
The previous one. Compressor.
expander? Okay.
Standard.
Because of this chart that we saw before. Whenever you are compressing a gas, you are always increasing the temperature of the gas because of the inefficiency of the system. When you expand, when you do the opposite, you decrease the temperature. So actually, that's a first indication that you say my result should be lower than the inlet.
Always decrease.
For expander, yes,
Compressor is always.
increase, yeah.